Someone left it last time, I think. All right, good morning. Let's slowly begin. We have one more minute to start. Because I was late yesterday, didn't get to introduce the way I'll be conducting. So I'll spend a few minutes, but after it's 9:05, yes, now. So there will be questions at the beginning of each lecture. It's very important that you read those questions and start thinking about it. And throughout the lecture, your goal will be to find answer to that. And at the end of the lecture, before you get out, ask yourself, did you get all the questions answered? If not, come back next time, right? And you will be asking me those questions. So I'll give you some opportunities. Let me just first tell you, the first question we asked was, what is the classical model? And we have been talking about that. The classical model is something that focuses on supply, inputs, productivity, technology, and gives answer to this question like, what will be the national income of your country? What will be the price of labor, the real wage, or price of capital, real enterprise? So it answers those kind of questions, right? It leaves out questions about aggregate demand, because it assumes that prices are flexible in all market, and whenever there is supply, the price will move to generate demand for it, right? Too little supply, price will go up. Too much supply, price will go down, to make supply and demand equal. That's their assumption. It's called supply gives its own demand. So that's the answer to classical model. By the way, model, you should know, is an abstraction of reality. It tells you a story about how things work. And we all have stories in our head. When you go and interact in the world, we all have some ideas about how things work. And we need that to interpret data. Because when you observe anything, you look at this room, what is happening, you really don't understand unless you have a story. Okay, yeah, this is a class going on because this will happen. There's some causality there. So story is nothing other than causality, connecting the dots in a way that, okay, this makes that happen, this makes that happen. You need that. You need that causal flow. And model helps you to do that. So in a structure of any model, a good model, you will have a bunch of assumptions, which comes from nowhere, you assume. And then we make some prediction. They are called proposition or statement of the model. So that's what we're going to do. So classical model assume prices are flexible. It comes from nowhere. We just assume that, right? And then we build this theory. So there is Keynesian model, which will come, and I'll elaborate more tomorrow. That focuses on demand, okay? And how it does it, you study it in stage 1, and it says, doesn't matter what the supply is. If the demand is not right, we're not going to get there, so you have to change the demand. So how do they, what's the purpose of them? Because they don't believe in flexible prices. See, the flexible price is an assumption, is a prejudice, right? Keynesian people say, no, prices are not flexible. There are lots of reasons prices are rigid. And again, we don't ask question their assumption. We take that, and then we say, okay, if that's the case, what happened? So we'll talk about those two things. I am going to add one more layer to that, and then we finish answering that question. So the answer is done here. If you want to write it down, the answer to question 1 is already done. So classical model is about supply, Keynesian model is about demand, and they both help us to interpret data. And the key difference, I said, prices are flexible by assumption, and prices are rigid by assumption. But there's a name for it. So when everything is flexible, that means the economy can move around any way it wants to go. It goes where really is fundamental, right? So if you want to go to a place, in the morning you are driving, and you can just go around any way, you reach the destination. The destination is your fundamental. That's the economic fundamental. And we'll talk about various fundamental. National income is a fundamental. Real wage is a fundamental. So when prices in all markets are flexible and economy reaches its fundamental, that condition we call long run. Okay? So why don't you go in the long run? That means eventually, ultimately, right? Somehow, it's kind of red herring. There is a time element there, right? The sense of time is really unnecessary. Okay? We should not think in terms of time. If it is flexible, you go there. If everything is flexible, instantaneously you can go there, right? Like a Star Trek, beam me up, Scotty, you go there, right? If you have the machine to just go there. So time is not the issue, okay? And also, if everything is stuck, you are stuck in a depression, no matter how long it goes, you are not going to go there, okay? So in that sense, this long run and time should not be associated. Long run simply means flexible environment so that you can go to your fundamental. On the other hand, economic theory, Keynesian theory says, well, if things are not flexible, you are stuck. You're stuck in a traffic jam. So you're there. So what is that condition? That's a short run. We are stuck there. We are not into, we didn't reach our destination. So what happened then? Well, there are some things to study. We study Keynesian model for that. We call that short run. Short run means temporary equilibrium or temporary outcome, right? All right. So with that, let's just go back where we finished. Actually, what I'm going to do, I'm going to just focus on the idea of measures of different productivity, and then I'll revisit the answers, but I'll be using graph. So from now on, there's another thing I should say. Bring pieces of paper, like A4 size, lots of paper. Those will be drawing as we go on. So before we do that, we're going to answer the second question, measures of economic productivity, and what fundamentals determine these three things, right? So before we go there, I'm going to just remind you quickly what we did last time. So I'm going to bring with this production function. Okay, so that's the production function, right? We talked about pizza. Today let's talk about, we already have labor here. Maybe I can just cross it out and make it capital. Uh, let's talk about restaurant, right? So on the horizontal axis, you have lots of restaurant, and I'm going to use a piece of paper that I printed, but you can use whatever you like. It is the same graph, but I'm going to just cross label and make it capital. Just for a change, right, capital. Okay, and you can think about number of restaurant. Okay. So what is the output of the restaurant? Now here is a catch. You have to think about, it's not just number of dish you serve. It is actually. So it's not the number of dish you produce, but it's the number of dish you serve, right? So let's say, give it 1,000, maybe 10,000, 20,000, 30,000, 40,000, 50,000, 60,000. These are the number of dish you serve, right? And there's the number of restaurant in a town. So over the year, right? Okay, so production function is saying that if you have one restaurant, you serve 10,000, two restaurants, 20,000, etc., 8 restaurants, 50,000. So one thing is clear, if you have more restaurants, you serve more customers, you serve more dishes, okay? That's clear. What is not clear is why, when you build an extra restaurant, say from 1 to 2, you increase number of serving by 10,000. But if you increase, say, 2 to 4, 2 more restaurants, the number of serving is still not going up by 10,000. So when you build more and more restaurants, the additional plate that you can serve is not growing proportionately, it's going less than proportionately, right? Can you tell me? Does it make sense? Why would that be the case? Give me a reason. You observe the data, how do you interpret the data? Right? Without using a jargon, I'm sure some of you know that law, but let's not talk about the law. Let's think about facts. So I'm going to do the following. While you think, I'm going to take this point, I'm going to call that, say, point A. And let's pick another point which is okay, say 3. Will be around here. So point B. So from A to B, I first run. That means I increase number of restaurants. By the way, I'm going to use this symbol delta to say either increase or decrease. Yeah. Oh, okay, I see. Right, thank you. Okay. All right, so let me just draw your attention to this symbol. It's a triangle, right? It's a Greek letter, capital letter called delta, okay? So this, in mathematics, refers to change, increase or decrease, right? So whether it's increase or decrease, I'll show you by plus or minus. It will always be increase in this class. So when you go from A, if you want to go from A to B, you walk along. So this is a coordinate geometry. You go to the right horizontally. So you walk 1 to 3. That means you're building 2 more restaurants. So additional change here will be 2. So if you call this K capital, so this will be delta. So this is change, you can write. Sorry, change. And this is delta K, because I'm changing capital, number of restaurants. 3 minus 1, so it's 2. right? So it's plus 2. Is everyone okay with that? Okay. So if we increase 2 more restaurants, how many additional dishes we can serve over the year? Well, you can go up there, 10,000 and maybe halfway through, so 15,000. So this is, rise, and this is run, people say in high school. So this rise, so additional output, now it is delta y, is going to be, say, 15,000. Right? So now if I join these 2 points, A and B, this should be a straight line. It will make a slope, right? And that slope is measured typically by this angle. And in high school geometry, you must have learned that this angle is proportional to the ratio of these 2 numbers, rise over run. And we call that slope. So we measure the slope of this line. And this slope is going to be very important in economics as you go and in this paper. So you should know. So this is slope of this production function in this area is delta y over delta k, and that in this instant is 15 over 2, which is 7.5. Any question on this? Okay, so now I'm going to do something. It's not calculus, but it is as good as calculus, I think. But you tell me. So I'm going to say, that 2 lines which are parallel, they make the same angle. So I'm going to show you here. Think about this 2 lines. If you have k here and y here, same axis. 1 line here, and then another line. They are parallel because the angle they are making with this axis are the same. If this angle is x and this angle is x, they're same. So these 2 lines are parallel. Okay? So I'm going to ask you to imagine this line that's joining A and B. Draw another line inside that which will be parallel to that. Now, at the risk of getting things messy, I'm going to use red line. Suppose I'm going to use this too. So this line, I can call that A prime and B prime, has the same slope as AB. So that means the slope is 7.5, still now, because they are parallel. But it's going closer and closer. And you can imagine pushing it further so that those 2 points, A prime and B prime, overlaps on that graph, on that thing, and it will be tangent. It's called tangent. It's just touching it, right? Not cutting it. So I'm going to use this color green. Green is going to be always used for some new concept. You possibly have already seen color. I'll explain them. Green will be new concept, and blue you already have learned, and red some question mark. Okay, so now if I do that, so suppose I push it forward and it touches here. So when it touches, it becomes parallel to that line AB. So this slope will be still 7.5. Now, let's call that point C. The slope of this production function at point C is 7.5, right? I'm making this conclusion, and you please raise your hand if you have any question about that. Okay? How many of you understood 90% or more the slope at C is indeed 7.5? Show your hand. Okay? Most of you. Some of you have doubt. Please make sure in the tutorial, ask the tutor, and make sure you understand that. Okay? So when I say slope of a production function at a particular point, I'm really taking 2 points near that point, on two sides and calculating rise over run. What am I calculating? I'm calculating the ratio of the rise over run. Now, economics. What is the ratio? Change in Y, additional dish the city serves to its customers per additional restaurant. If you increase 2 restaurants, if the council allows 2 additional restaurants in the city customer will be able to have 15,000 more dishes throughout the year. So that means marginal product of that capital, that means additional output, additional dish generated by one more unit of capital is 7.5. So what is 7.5? It is a marginal product of capital at that point. So this now you can write, you already know what marginal product is, so I'm going to say this is the marginal product of capital at C. Okay. Once you understand that, let me ask you the question I already asked. If I draw another slope, this time it will be blue because you know what the slope, suppose at this point, say at 8. So when you have 8 restaurants in the city, the marginal product is given by this slope, and you can see the slope is now flatter. You've got to use your imagination. If not, just draw those 2 lines, and you will see it will intersect, and you will see this slope is flatter, right? That means it makes smaller angle, right? Smaller slope. The slope is smaller. So all I can say that this is here, if you say at this point is D, so you can conclude that MPK, which is the slope at D, is, here's the question, less than MPK at C. Well, you can say that's true because you drew the graph that way. If you drew a graph like a straight line, if production function is straight line, MPK will not change. It will be the same. Or if it is the other way, which is called, it is called convex, and if it's non-convex, the other way, it bends the other way, then the slope will be higher. So you might say, yeah, I drew it that way. Okay, that's fine. Forget that. Is there any economic reason to justify that? Right? Again, don't use the word law if you already know. There is no law. There's logic. So why would you expect marginal product at D to be lower than marginal product at C? Or, put it differently, let me spell it out. Why would you expect if a city council allows 1 restaurant or something in between 1 and 3, any restaurant, and if you increase a restaurant from say 2 to 3, the number of dish served over here will go up by 7,500. But if there are already 8 restaurants, and if you allow 1 more restaurant, the number of dish served will go up, but not by 7,500, much less, maybe 5,000. Why is that? Raise your hand if you know the answer. Yeah. Or again, you answered the last time too, right? What's your name? Dylan. Dylan. Yeah. Dylan. Okay, Dylan answered the last time question. I'll come back to you if nobody else. Try. Is there anyone who did not follow the question because my accent is different? Raise your hand. I'll repeat. So everybody understood the question, right? Question is, when the council allows 2 restaurants, and the 3rd restaurant will generate 7,500 dish served. But if the council already observed 8 restaurants and reviewing application for the 9th restaurant and thinking how many dish will be resulted from that, the conclusion for the economist they hired, one of you will get a job, they say, oh, it's not going to be 7,500, it will be 5,000, less than that. Why would you say that? Anybody? Okay, Dylan. Excellent. That is very good. So what am I changing? Okay, the answer is, Dylan said population is not big enough, but I would say population remaining the same. Right? Not necessarily big enough, remaining the same, strictly. But I understand your sentiment. So what am I doing here? I'm increasing capital while labor is constant, right? So the output, which is the number of dishes served, is going to be served to the same group of customer, right? Now clearly, more restaurant, more choices, more people will go, but the same number of people, so the additional customer you can attract is going to be lower and lower. So in other words, like the pizza example I gave you, if you have the same number of oven and desk and car, if you increase number of employees, the additional product, marginal product of the last employee will be smaller. Exact same way, if you have the same size of the population, if you increase number of restaurants, the marginal product, which is the number of dishes served, will be smaller. This is called the law of diminishing returns to input, which simply says that if all other inputs remain constant, if you simply increase one input, all the other input become crowded, congested. So the increment of that input become less and less productive. Okay? Any last question about this? Okay. So this is law of diminishing return. Any question? Extremely important. Not this chapter, necessarily next chapter, the following chapter. So now I'm going to answer you a couple of other questions. So we talked about marginal productivity. I could use this graph. Maybe I will, just to show you. If I join the origin and another point, say this point E, if I join these 2 points, just a straight line joining them, right? Oh, I don't think I can do, but I'll try. Okay, it's a straight line. What is the slope of this straight line? That's my question. Right? Again, rise over run, so you have to see how I go to E. So you have to drop a perpendicular from E to this axis, come to 6, right? So slope of this line is how much? Raise your hand quickly. What's the slope of this line? Sorry? How much? What's the length from, okay, let me give you another letter. F. What is the length of EF? This is coordinate geometry, so I'm doing it just to see how well versed you are. If you are not tutorial, very important, you have to be able to read from the graph this coordinate. So EF, what is the length? Yeah, okay, I'm sorry. This is halfway, right? That's possibly a problem. Yeah, approximately between 40 and 50, you can say, right? 45 is good. And the length of OF is 6, right? So if it is 48, it will be nice to divide, but in 45 over 6 is okay. So the slope will be equal to, so this is 45, and this is 6. That's the slope, right? But doesn't matter the actual number. This slope I can write in terms of letter y, 45 is the output, divided by the input, which is k. And that is called average product. Like you have the marginal product of k, you have average product of k. So at that point, E, you get the average product of capital. So what is average product? Total output, 45,000. Total restaurant, 6,000. This is another measure of productivity. Clearly, if you want to go the marginal product at that point, you can draw a line and you get marginal product of capital at E. Okay, and so this is the average product at E. So now my question, that's why I did it by red. At E, you have two measures of productivity. Marginal product is just the tangent. Average product to join a line from the origin and take the ratio. Now, if you just divide the marginal product by average product, what do you get? Well, that's fun for mathematicians. They just want to see what do you get. Keep that question aside, because that's not really economically intuitive question. So I'm going to ask you a different question. We have two measures. As a council chairperson asking you to give you an idea about the merit of building another restaurant, right? So one way you can say, well, the average productivity will be 45 over 6. The marginal product will be some number there between 7.5. It will be lower than that, so maybe 6. But there is another measure council can ask. Council can say, well, if you increase one more restaurant, so 1%, if you increase the capital stock by 1%, by how many percentage output will go up? So that is the elasticity. Okay, so if that is the question, how do you answer that? So I'm going to just develop that concept and then we'll move on. I know this is basically technical, but once we do it, a lot of other things will be much easier. So the question is, elasticity is defined by percentage change. So I'm going to put percentage change of y divided by percentage change in k. And I'll define what percentage change symbol means. This symbol is simply change over the initial. And then you multiply by 100. Okay, so let's just say that's equal to percentage change of y will be change of y divided by the initial y and then times 100. And now divide that, sorry, this is an equality, it should be percentage change in capital. Question? Okay. This 100 will cancel, right? Now, I'm going to do some algebra, but I hope this is not a big deal. You know, if anything is at the bottom, and if you want to take them to the top, you have to flip it, right? So if it is, or maybe I'll do it that another way. I multiply numerator and the denominator by the same. So I multiply the numerator by y, and the denominator also by y. So what we have in the numerator, this y will cancel. So I'll only have delta y. And in the denominator, we'll have delta k, but you have y here on the top and k at the bottom. So I will just say this times y over k. Is everybody okay? Raise your hand if you didn't follow this step. Okay? So then the next step, the last one. I'm going to multiply the numerator. Well, I think you can already see that. So I'm going to divide the numerator by k, delta k. I'm going to divide this by delta k. And I'm also going to divide this by delta K. So what do I get? This will cancel. So I will get at the numerator delta Y over delta K, and the denominator I get Y over K. And now remember, the delta K over delta Y over delta K is marginal product of capital. And this is average product of capital. So this is the formula. If E is elasticity, this is something you knew, you will just learn, and you should remember that. This is very, very important and going to be useful. Okay? You could have used another expression of this elasticity, which is, or you could have used this formula to get another result, is that if you multiply both sides by average product, then what you get? You get E times average product equal to MPK. Now, people who do not know calculus will find this handy. So what is MPK? MPK is delta Y over delta K. If you know calculus, I'm saying one sentence, that if you take the limit as delta K goes to 0, it becomes smaller and smaller, it becomes a derivative of Y with respect to capital. So you can simply take the production function and differentiate with respect to K, and you get that. But if you do not know calculus and you just ignore what I just said in the last 1 minute, use this formula. So you get the MPK simply by multiplying the elasticity of a production function times the average product, which is Y over K. Now you might say, well, how do you get the elasticity? And that's what I'm going to talk to you with now. It's going to be very easy if you just follow one thing. Okay, so what I have done here, I'm going to put them on canvas, but I'll do something also from, this is from last time. I'm going to show you this has something which I can quickly use. So this is a production function. I did these slopes, etc. MPK is that. If you have a production function, say Y equal to 10 times K to the power half, this is the elasticity. So whenever you have something to the power, it's elasticity. I'm asking you to just to know as convention. So typically, you will have a production function which will have powers, and these two powers may add to 1, and then it will have some meaning for that, but doesn't matter at the moment. So if you want to do the elasticity, that's it. So if you want to get, for example, the production function is Y equal to, let's just throw in an extra parameter A, and I'll explain what A is, K to the power half, L to the power half. I am saying the elasticity of K is not showing, which is percentage change in Y over percentage change in K, and in symbol you can call it elasticity of Y with respect to K, in this instant is half, because this is the elasticity. Okay, if we know that, what is the marginal product of capital? MPK, which is del Y, del K. Can anybody answer that who does not know calculus? Or you have to reveal that, right? So, okay, anybody. Here is the formula. If elasticity, that E, is the same as this E, and given the production function, you have this half. So the marginal product, you have a chance, if you know calculus, this Y, you can differentiate this Y, you have to take partial derivative with respect to K, or use this formula. So MPK is equal to E which is half, okay, maybe I should use blue, which is half, times APK. What is APK? Y over K. So half of Y over K, right? All right. One last thing, and then I'll go. I threw that A here. What is that A? Well, in terms of mathematics, you can see if K and L remain constant, that means number of restaurants, number of people in the city remain constant. You may still have number of dish served increasing. Here is the reason. Imagine you are living in a city which never heard of dishwasher. You can. There are places like in the world. And suddenly you introduce dishwasher. Or an oven where you can cook a lot of things much faster. Then, immediately, that technology, number of restaurants remaining constant, will increase number of dish served. And you might say, well, the same number of people, how could they eat more? Well, we are assuming number of people remain constant. If food prices drop, they will be buying more. And if you have dishwasher, machine generated oven, cost of production will go down, so prices possibly will fall, and they'll go. So we are assuming all those things, if this bothers you. But what does it mean? Why is going up while the number of restaurant constant, number of population constant? How do you capture that in economics? So we throw that term in. We call that A. We denote that by A, but we call that total factor productivity. We talked about marginal productivity of each input. We talked about average productivity of each input. But now we are saying this is total factor productivity. If A increases, not only the productivity of capital will go up, productivity of labor will go up at the same time. It's called total factor productivity, or TFP. Okay, so that's all about answering the first question. So let me just get that question. Okay, so this actually relates to today's question as well. So let me, those will be the question for today. But let me connect them. So my new questions will always relate to the previous question. So we're talking about what are the economic measures of economic productivity. So the answers are marginal product, average product, elasticity, which is the ratio of those two, MPK over APK, and now you have TFP, total factor productivity, which I said A in a production function Y equal to, say, A. Now I had K to the power half. Now I am taking the liberty to change to a general letter, right? I could say little a, K to the power A, and L to the power B. Okay. Okay, yeah, sorry about that. This is, I have to keep looking. Thank you. Okay. So all I said, these are the things. So let me quickly quiz you and get the answer. So what is the value of elasticity of output, I mean percentage change in output with respect to labor? And what is the value of elasticity of output with respect to capital? Raise your hand from this side first. Try, quickly. Somebody must know. What is the elasticity? Yeah. B, that's the correct answer. It's a power, right? So this B is the answer, correct. Now, from this side, elasticity of capital, elasticity of output with respect to capital. If you increase capital by 1%, by how many percent output will go up? Yeah? Always remember, elasticity is like a cap, right? Or if you tie your hair, the knot, right? That's the elasticity. So what is that? A. See that? A is a nice hair knot on K. Always remember that. So that's this A. Now this, obviously, I am simplifying math into art, but it's going to work throughout the economics degree. You can get that. Once you know math very well, you can figure it out later on, right? Why do we, okay, so what's the name for your general knowledge? If you have a production function where the slope at any point divided by the slope of the line joining origin at that point, the elasticity, is constant, then we call that function constant elasticity of substitution, CES production function. Then you have that property. And Cobb-Douglas production function is a special case of constant elasticity of substitution. Cobb-Douglas production function has an added property, which is what I just showed you, that whatever is on your top is your elasticity. Okay? So this feature, this artistic feature, true for Cobb-Douglas technology. And since you're going to use only Cobb-Douglas, why not remember that? That helps us to calculate the marginal product of labor and capital. So let's see if I can get an answer from you. I'm going to ask you, if you know calculus, you can take the derivative, but you may also choose not to take the derivative and answer right away. So if this is the production function, what is the value of marginal product of capital? Okay? Can you answer that? Given this production function, what is MPK? Middle, right? Dylan, you can go first if you like. What's the marginal product of capital? Okay, everybody. Yeah.
Little a, capital A, and then the K and alpha, L.
A times?
And then capital A.
Okay, I don't want to use, okay, so you are spelling it out, right? But how about use Y?
Oh, right.
So it will be?
Times Y.
Y divided by L. Right? That's in it. So it's elasticity times average product. That's it. Right? Now, this one you need to come from here. Right? Marginal product is elasticity times average product. Right? So I wrote K here, so I should have written Y and over K. But L will be the same. Okay, that's enough of. Any other follow-up question before I just switch? Yeah.
With the marginal, that first one, marginal product of K.
Yeah.
Why is it?
Oh yeah, I made a mistake. I just made a mistake. Thank you. Sorry. So, correct answer should be what?
A times Y over K.
Yeah. Pay attention. Thank you. Yeah. Y over K, right? So MPK, in case anybody is confused, is equal to A times Y over K. And MPL equal to B times Y over L. That's, you just learned. And TAP in this case is A, right? It's overall. But you notice TAP is already in A, so you are possibly spelling out Y. If you spell it out, A will be there. So when A increases, marginal product of capital increases. Similarly, when A increases, marginal product of labor increases because A is inside Y. In other words, whenever total factor of productivity increases, better technology increases productivity of everything. You know, suppose you did not have Wi-Fi, you introduce Wi-Fi, productivity of labor, capital, all will go up. Okay? All right, so now today's question, and it's almost answered. Question was, what are the three, not three, actually it will be four now, measures of productivity, marginal, average, elasticity, and TFP. Okay, technically speaking, there are three, average marginal and TAP, elasticity is simply the ratio of those two. So I'm going to write down elasticity is simply MP over AP. Let's look at the time. Right? And you have TAP. So TAP increases all of them, right? So how they are related, you can see the connection there. Okay. Now, I'm not going to touch that. This will be the first question tomorrow we are going to talk about. So we just learned various measures of productivity. We'll connect, now stay there for a couple of minutes. We're going to connect this productivity to real wage, national income, real enterprise of capital, and we'll first begin with the product exhaustion theorem. So I'm going to put on canvas a couple of handouts which you should print and may bring, and we will try to answer first this question: how do you get equilibrium, demand equal to supply in the classical model, and how TAP can affect that. So I'm going to put in the canvas this thing to summarize what I did about elasticity. So take a printout of that, and some handout I will go over. You will see when you open it, to prove one theorem. So this is the last sentence I'm going to say. The theorem is, when firms maximize profit and pay according to marginal product rule, total income of labor plus total income of capital must be equal to total national income. It's called product exhaustion theorem, right? And I'll have a handout about that too. So read those handouts, come back, and we'll continue. All right, see you later. Hi, Deepan.
The MPL equal to the APL multiply E. And MPL is...
So this is the formula.
yeah,
You can figure it out from there, right? Yeah.
the MPL is the slope of a point, right?
At a point, once you draw production function against L, then slope at any point on the production function is the MPL at that point.
Okay. So in this formula, which point is we talking about?
Which point? So this is the, okay, any point. So there's a graph like that also I showed at the very end. Where is that graph? It should be here, I guess. Yeah. So here, so think about point C. So elasticity at C, if you join O and C, you take a slope of that and divide the slope at C by that slope, you get the elasticity. Okay?
Thank you.
Yeah, okay. Hi.
Can I just take pictures of
This?
of the few formulas?
No, I'm going to put it on canvas.
Oh, okay.
All of them.
Okay, yeah, just so that I can I understood.
Yeah, yeah. I'll scan them
Yeah.
and put them on as lecture handout. There'll be a folder. Okay?
Thank you.
I don't call, I don't know, lecture notes, I call them. Yeah. Yeah. You can ask, you can, oh, by the way, I have another class to teach. So today, always a bad day, I have to run. But tomorrow after lecture, I can talk. But you can ask a quick question. I'll take one from you and one from her.
I have a question about the graph.
Okay, which graph?
Yep, not that one. It's the first one. Not this one.
Yeah.
For the slope for this one,
Mm-hmm.
isn't it, it's 17 divided by 2?
Oh my gosh, what did I do?
You got for like
No, 15. No, what is it? Okay,
it's like 27 divided by 2.
so okay, I made a mistake here, huh? So, okay, this time, you should tell me at that moment. So you are right. So from 10,
yeah.
and this is going 15. No, this
It's
25.
Yeah.
No, that's fine.
Oh, because 3 is here, and then,
No, we are measuring capital on this axis,
yeah,
output in this axis, so
Yeah.
don't add them. So at that point,
yeah.
number of dish served is 10,000, right? At that point, number of dish served is 25,000,
But
right?
how do you get 25,000?
Okay, it is in between 20 and 30.
But 3 isn't it this point?
Okay,
So
so
why
what?
is that this point?
Oh, okay. So think about this point is that.
Oh, okay.
Okay, think about this point is that, right?
Okay.
Yeah, because when I drew, yeah, you were right.
Oh, okay.
Okay, so I'll just cross out.
Yeah, okay.
Okay.
Yeah, just leave that confused.
Yeah.
Thank you.
Yeah.
I'm not sure why that,
Okay.
yeah, why should we,
Hmm?
why should we keep the, is it here?
Oh, that's in tutorial. They will talk about it, right?
Okay.
Yeah, it is it's a scalar.
Yeah.
Okay, you can think about 2, z equal to 2, right? It's simply saying if you multiply labor by 2, then double it, capital by 2, double it, then output will be doubled. So this multiply by 2. So this is a property. Huh? If it happens, you call it constant return. If it doesn't, then you don't.
Okay.
Okay? You're welcome. Yeah, welcome.
Can I just set it up?
Yeah, yeah. Sure. I'm sorry. Yeah. This is a bit slow, right? That one?
Yeah.
All right. Oh, sorry. That is loud. All right. Thank you all for coming. Now, people at the back, can you hear okay? Good. Yeah. Great. Now, I understand from Monday that in the overflow room, apparently if I move too fast, the focus actually goes in and out. But I can reassure you, I am actually in focus. So I'll try and move less for those people in the overflow room. Right. So thank you all for coming. So we'll probably continue on where we left off from Monday. And we'll start essentially looking into some of the more technical stuff as we move on. So if I can get you to just move to page 7 of the course book. Now you see, despite all the rambles that I gave you on Monday, the study of electrical and digital systems really comes down to two things. And you would have noticed I've written there, it's just the manipulation and interpretation of things. The manipulation of what? Essentially just the manipulation of electrical quantities, that's current and voltages. And the interpretation of what? Again, literally interpreting what those voltage and current means. So it's quite a powerful thing if you think about it, because this interpretation completely depends on us, right? Given the output of a temperature sensor, for example, which it couldn't just be a voltage, but we decide what that voltage means, right? For example, if we want the output, if we want to display the output of an electrical sensor, well, we simply need to design electronics which maps whatever voltage it out to some sort of a number corresponding to, say, the temperature. Likewise, if we are interested in actually controlling the temperature itself, well, we just need to somehow design some sort of electronics that maps that voltage to drive, say, some current through some resistive heating element and thereby generate heat, right? So in both cases, we're manipulating the voltages in exactly the same way. In what way? Simply using electrical circuit. Right? So the manipulation is standardized, but the interpretation, well, we decide what it means, right? In the one case, we are deciding the on and off state of these LEDs that displays the actual measurement, while in the other cases, we're actually controlling the current, which controls the temperature itself. Right? So similarly, you know, at the lowest level, if you sort of read the other example I have, at the lowest level of the internet, all you're doing really is transmitting numbers. Transmitting numbers in terms of voltages and currents, right? And we do that through essentially using receivers and transmitters, or what we call transceivers, which really are just electrical circuits at the end of the day. But what that number means, again, we decide, right? As long as we agree, in earlier cases, we have a pre-agreed convention, then these numbers can mean anything, right? It could mean an email, it could mean a letter, it could be an image, or simply just a number. Again, the main point is this manipulation really comes down to just using electrical circuit. So at the end of the day, hopefully you can see, if we want to start understand electrical systems, all that's important for us is a few things, 3 things essentially. We just need to understand essentially what these electrical quantities actually mean. In other words, well, what does a voltage actually mean? What's a current, right? What's a resistance? If you haven't figured out yet, essentially all you need in electrical engineering is just voltage, current, and resistors, believe it or not. But you'll see that a bit down the line. But more importantly, we want to know how they actually behave in an electrical circuit. And finally, you know, well, how do we actually probe these quantities if needed, right? Given a circuit, do I have the ability to analyze and figure out what these voltages and currents are? Only once we understood that, then we can design circuit to manipulate these quantities to whatever the hell we want it to do. So that's my overarching goal in this next few weeks. If I can get you to look at the table of content, you'll realize that's essentially what the start of chapter 2 is about. So I will actually spend a few lectures right now and the coming ones, probably around 4 or 5 lectures, just going over these important concepts that you probably had an earlier exposure to during high school, but I understand that we might all have a different background, so it's important that we get the fundamentals correct before we moving on any further. I will then spend the next, essentially, probably around 5 lectures as well, going over these tools, what I like to call the tools of the trade. Again, some of these might be familiar to you already, but some of them are not, especially sort of the later 3 down there. I would then like to essentially change perspective and jump into chapter 3, essentially get a head start on this idea of sensors, so the monitoring technology that we talked about on Monday, and this will take probably around 3 lectures, and before Bill will take over and cover the remaining part of the smart engineering as we go. So that's the plan, that's the attack plan that we're going to take. So let's probably get underway. Now, you might be wondering, well, why is this so important? Well, it's important because if you notice, this idea of voltage and current, while you might have an understanding of it, in fact, it's especially important that we all become fluent with these terminologies and how we actually represent and describe these quantities. Why? Simply because they form the language of everything that we practice and do. You see, it's not very useful if you were to ask a question in engineering saying, I don't know what that thing in that rectangular looking thing is, right? No one will understand what the hell did you mean. But if you understood these quantities enough that you're fluent with this language, then it makes sense when you say, I don't know how to determine what the current through the resistor is. But the only way you can get there is we all have a firm understanding of what these underlying quantities are. And essentially, if we don't have a concise way of articulating what we wish to convey, well, then we can't really do any sort of engineering. So I apologize if these seems trivial to some of you, given that you already grasped this very well in your earlier exposures, but I just want to make sure that we are all on the same page. So we're going to start off talking about essentially charges and current. Now, back in the days, somebody probably told you this notion of electric charge, right? And they are kind of weird things, right? For example, if you put 2 charges together, they could either repel or attract, right? And from that, we essentially inferred there are 2 types of charges, right? And in fact, that's what gave us to define this notion of positive and negative charge, thanks to Mr. Benjamin Franklin, right? He arbitrarily gave the label positive and negative when we realized there are essentially 2 types of charges. What else did we figure out? Well, we also figured it out experimentally, thanks to Mr. Coulomb, that how they actually behave, right? We figured out if you put 2 charges together, well, the amount of attractions or repulsions actually depends on 2 things, right? It depends on the size of the charges and also how far away they are. The further away they are, the less force they have on each other. And this is something we also figured out. And it's something that's called the Coulomb's law. You may have seen it before. Surprisingly, believe it or not though, we have never understood what a charge actually is. But we only know what possesses charge. For example, we know electrons, they possess negative charge, right? Likewise, protons, we know they have positive charge. But it turns out protons are not the only subatomic particles that possess charge. There are now particles such as positrons. Not sure if you heard about those. They're very hard to observe, but we know they do exist. That actually, surrounds us, right? But we can't really observe that, right? They're very hard to find. So based on what we can actually observe, we essentially associated the flow of charges to the movement of electrons. Now, surprisingly, we also don't know what an electron is, right? We know what a proton is. Essentially, we figured out that it's made out of essentially subatomic particles known as quarks, right? So 3 of these quarks makes a proton. In fact, more recently, quantum field theorists suggested that these quarks might not actually be particles at all, right? They are just ripples in what's known as a quark field, right? And an electron, well, it turns out that electrons not actually made of anything smaller, right? Again, they are just these ripples in what's known as an electron field, and these fields actually extend throughout the entire universe. Right, so that's a problem, right? We don't know what an electron is. We don't know what a charge is. What the hell are we doing? But it turns out, look, we don't need to know what they are. The reality is, it doesn't matter what the reality is. As long as we have a precise way of describing it, right, that's good enough for us. Because as engineers, we're just making use of what we can observe, and we leave the technical details to the physicist. Right, so we understood, okay, here's an electron. We don't know what it is, but we know how it behaves. And there's a natural tendency for it to be attracted to positive charges. And that's when we got clever. We realized, well, what if we figure out a way that we could separate the charges, the negative charge, the electrons, from the positive charge, whatever that is? Well, now we have essentially gave electron energy, right? And we do this through various means, right? Battery, for example, is exactly one such thing, right? It's just an electrochemical reaction in there that essentially separates the electrons from its neutral state away from its positive charge, thereby giving it energy. Likewise, if you studied physics in high school, you'll notice if we rotate a conductor in a magnetic field, well, that generates separation of charge, essentially. Well, it generates a current, which we haven't got to, but there you go. Right, so then we figured out, okay, if we can somehow separate these charges, then we know essentially how to manipulate them, right? Because by separating these charges, if we provide an alternative path for it to flow, it will essentially go that way in order to return to where it wants to be, right? That charge neutral state, right? And that's essentially described in this diagram here, right? So there's some sort of electrical chemical reaction done in a battery, for example, that separates the charges, the electrons, from the positive charge. And by providing this alternative path to it, well, now that electron will want to flow through that path back to where it wants to be. And in doing so, it provides the energy that it has gained to the device before returning to the start. And that's all a circuit is. If you even realized, a circuit is just a series of connections for the electron to flow around, gain energy, lose energy from the sources or the devices, and do whatever is necessary to get there. So if you really think about it, electrical engineering, we are quite a dirty profession. Right? All we're doing is we're manipulating these electrons, for which we know how they behave, to do our biddings, and they are at our mercy. Right? So it's quite dirty if you think about it like that. But look, that's where we are now. Right? So that's how it is. And so the way we measure charge, you've probably known as well, it's measured in coulombs with the symbol C. And the electron is the smallest freestanding particle known to date that possess this charge, whatever it is. Remember, we don't know what it is, we know how it behaves. And an electron has approximately 1.6 times 10 to the negative 19 coulombs of charge. Now, believe it or not, 2 months ago, we've actually updated the exact value of this. So on 20th of May, we updated this exact value to 9 decimal places, because why not? And that's due to adjustment of Planck's constant. You don't need to worry about that, right? Now, in other words, right, if an electron has 1.6 times 10 to the negative 19 coulombs of charge, 1 coulomb of charge, that means, obviously, we have 1 divided by 1.6 times the 10 to the negative 19, which is 6.3 times 10 to the 18 electrons. Do you need to know that? Probably not, but there's just for your information. Okay, so, that's charge, right? That's how it is. That's how a circuit works. We have a charge electron that's separated from where it wants to be. It flows around the circuit, gain energy, lose energy, delivering energy to the device. That's it. What else do I need to know? Well, what you need to know is, you see, hopefully you realize that all electrical devices requires a continuous supply of energy to function, right? If you want a heater at home, well, it's continuously converting that electrical potential energy into heat, and so it must be receiving some sort of continuous energy from somewhere. And from where? From the electrons transporting the energy to it. Which means what we're actually more interested in general is essentially the rate at which these charges flow. And so you'll essentially read about that in the paragraph down here. Right? We are generally more interested in the rate at which charge flow because that gives us an indication of whether the device is working or not, since all electrical devices requires a continuous supply of energy to function. Right? And now, because we're more interested in the rate of flow of these charges, for example, I want to know how many charges is flowing past this device in 1 second. Right? Essentially, how many coulombs of charge per second. Now, the minute you know it's a rate, you know from your high school calculus, it probably relates to some sort of derivative, right? So the rate of flow of charges give us an indication whether the device is working. Because charges are flowing through it continuously, it's delivering energy to it, the device must be doing something, right? It can't be receiving energy and not doing anything with it. Right? And, which is fine, until you realize you've got to explain that to someone. You've got to keep saying, the rate of flow of charges through this device is 3 coulombs. Oh no, the rate of flow of charges through the device is now 2. Nope, the rate of flow of charges, it becomes a mouthful. So instead, someone got pissed. Ampere got pissed, Mr. Ampere. So he gave a definition. Right? He defined the rate of flow of these things to just be called current. And that's essentially the definition, right? A current is just a rate of change of charges flowing through somewhere at a given time, right? And that's what I would have indicated over there. Right? And the unit for it, intuitively, if it's a rate of flow of charges, is the number of coulombs per second. But of course, back in the bad old days, when you come up with something, you usually put a name to it. So ampere becomes the unit that we convey for the rate of flow of charges. But that's all that is, right? A current just tells you how many charges is flowing through somewhere in 1 second at any given time. Are there any questions with that? Hands up if this makes sense. And this is so straightforward. All right, great. Now, what's the catch then? Well, the catch is in the next page. It's always good to start by saying, well, we screwed up. What did we screw up? Well, Historically, you see, thanks to Mr. Benjamin Franklin, who defined charges to be positive or negative, well, he believed that the flow of charges was actually attributed to positive charge carriers, right? But you understand, what did he know, right? He hypothesized this in the 1700s, whereas we only realized when that electron actually existed in the 1800s, thanks to Joseph Thomson, you probably heard of him, and our very own Ernest Rutherford, right? But that was in the late 1800s. So he hypothesized that that's actually the charge that flows is actually positive charge. But of course, we know that's not true, right? If you followed our discussion just then, it's actually the electrons that flows, right? The positive charge, which we can observe, are protons. They are happily stable in the nucleus of these atoms, right? So what that means is, conventionally, back in the days, a current, the rate of flow of charges, is actually thought to be these positive charge flow. And you know what? This is why you always consult multiple sources, because everyone took Benjamin Franklin's word for it, and centuries, all the work done, are based on this notion that positive charge flows. Right? For example, have you guys heard about a diode? You know what a diode is, right? If you haven't, essentially it's just this weird looking, it's a semiconductor device, but it's a device that allows current to flow one way and blocks the other. So it only allows current to flow one way. And you'll learn more about this a bit down the line. But this diode symbol, that direction is based on the current of the direction of a positive charge flow. What that means is, if this diode conducts, it actually takes the current to be flowing to the right, right? That's when positive charge is flowing in that arrow direction. But of course, we know when it's conducting, it's actually electrons that's flowing to the left. But nevertheless, right, we were idiots back then, so we took Benjamin Franklin's word for it, and this is why you never take authoritative advice, right? You always look at multiple sources when you study these things. The good thing, though, for us, right, if an electron's flowing to the right, that's equivalent to a lack of electrons flowing to the left, right, by relative motion. So other than the direction of charge flow, if we follow the conventional current, it actually had no impact whatsoever on the theories developed. So as a result of that, we ended up adopting the conventional current anyway. So essentially, in any circuit we draw, the current is the direction in which positive charge flow. So for example, in the circuit down here, we know the electrons will actually flow counterclockwise, but the current that we label is actually the positive charge that's flowing clockwise. Why didn't we make that change, you might ask? Simply because it's too much work, right? All the literatures, textbooks, whatever is already published, assuming conventional current, and there's just no point, given that innocent mistake had no impact whatsoever. Now, just a bit of nomenclature. The way we label current is with an arrow in the wires, right? I'm very against people who draw current outside of the wire, simply because sometimes that can be mistaken to mean a voltage. The other way we express this is using this sort of double subscript notation. If I write I subscript AB, that means the current flowing from A to B, right? So that's the order of from and to, right? So you'll notice the expression down there, they all mean the same thing, right? That's the current from A to B, which is the same as the current from B to C, which is the same as C to D and D to A. And in this case, it's all 4 amps. So that's as much as I would like to say about current and charges. So if you look at the example down there, it's a very straightforward, well, not straightforward, but it's just a quick warm-up on whether we actually understood what the meaning of this current and charges are. So if we look at that, you've got a current that's 0.5 amps. What does that mean? Remember, amps is just a shorthand because Ampere got pissed. It's just a unit for number of coulombs per second. So there's 0.5 coulombs per second flowing through a light bulb in a torch for 8 minutes, okay? We want to find the total number of charges that pass through in the light bulb in this time. How many charges are there be? Hopefully, see, it's not too bad, right? Total charges passed. What would that be? Well, I know there's 0.5 coulombs per second through this light bulb. It's running for 8 minutes straight. If I were to draw a graph, which you don't need to, but why not? I like graphs, right? It essentially looks like this. 8 minutes, that's the same as 8 times 60 for 80 seconds, right? And that's 0.5 amps. That's how it is. So how many charges has passed this time? Well, hopefully you can see it's the same as just 0.5. The unit is coulombs per second times the number of seconds it has passed, which is 480. Right, in this case, that gives us 240 coulombs. So there are 240 coulombs of charge that flow through that light bulb, delivering energy to it during that 8 minutes. Now that's just the intuitive way of seeing it, right? Obviously, the more rigorous way is if we apply this notion of the fact that a current is a rate of flow of charges. So you know from MM1 probably, if I'm given the current, I want to figure out what the total charges passed through is. Well, I just solved this first order differential equation, right? How would I solve it? Well, I integrate the current. Integrate current over when? Over the period at which it's on. So it's essentially 0 to 480 times the current, which is 0.5 dt. Right, so there is rigor behind this notion that current is the derivative of charges, because it allows us to figure out, well, this is the same as 480, which is 240 coulombs, right? Nice and easy. Now the last part also asks, well, how many electrons are actually needed to carry this charge? Well, we figured out one electron contain 1.6 times 10 to the negative 19 coulombs of charge. Do you need to remember that? No, right? It's stupid to memorizing these numbers. But the number of electrons must then be, well, if I got 240 coulombs of charge, each one of these electrons has 1.6 times 10 to the negative 19, then it's a matter of doing that division. And I believe it comes out to be roughly 1.5 times 10 to the 21 electrons. And that's it. So that's just a quick reminder of what these charges and current actually means. And hopefully that's not too bad. Are there any questions? Hands up if this is okay. Okay, good. So if that's okay, I would like to move on to the final thing that I will cover today, which hopefully will get you started on the assignment, which we will make available after the lecture. Now you'll notice the assignment might require a few more concepts that we haven't covered officially yet. Shh. Thank you. Now, we haven't actually quite covered officially yet, but you will definitely have seen it. But as we progress throughout the rest of this week and next, you'll be able to do it eventually. Right, so voltage is the next thing, right? It's the most commonly mistaken concept to people in general, right? I do ask Part 4 student what a voltage is. Believe it or not, they couldn't answer it. I'm not sure why, given they would have taken the same course here. Maybe because we're just terrible at explaining this. But anyway, so what's there to know after we know all a circuit is charges flowing around the circuit because we manipulated them to do so? Well, you see, as these charges flow through a device, they either gain energy or lose energy, right? They gain energy if this device is a battery, right? But they lose energy if this device is, say, a light bulb. What does that mean? That means actually, if we can somehow monitor the changes in energy of these charges as they flow through something, for example, if you look at the thing down there, if I can somehow measure that the charges, say a coulomb of charge here actually has 9 joules of energy, and I measure the thing at the bottom, and it turns out that each coulomb of charge there has 4 joules of energy, then that gives us an indication of how much energy the device actually used, right? If the coulomb has 9 joules there, each coulomb has 4 joules of there, then if the coulomb went to flow downwards, then it must have lost 5 joules of energy, right? So it's actually meaningful for us to measure this difference in energy of each coulomb of charge, of these charges. And that's what it is, right? So if we can monitor this difference in energy, that tells us what the device is using, right? Again, it becomes a mouthful when you want to convey to someone, right? The difference in energy per coulomb of charge across this component is 5 joules. The difference in energy across each coulomb of charge in this other component is 6 joules. Someone got pissed, right? Who got pissed this time? Mr. Volta, right? Alessandro Volta. He got pissed. I don't want to say this mouthful thing, difference in energy each coulomb of charge across this. So he gave it a definition. He called that mathematical difference between each coulomb of charge across 2 points to be called a voltage. A voltage is just a mathematical difference. It is not a flow, right? So I'll highlight this, not a flow. Some people tend to think voltage is some sort of quantity that flow through a circuit like a current. Sorry, like charges, right? Charges flow, a voltage doesn't, right? It doesn't make sense to say a voltage flow because a voltage is just a mathematical difference. What is the difference of? It is the difference in the electric potential energy of each unit of charge between 2 points, right? And because it's a difference in potential energy of each unit of charge across 2 points, sometimes it's also known as a potential difference, right? But I hate all these different names for it, right? In the future, if it confuses you, just replace voltage whenever you say it as a difference in energy of charges, right? Or actually, it's each difference in energy of each unit of charges, which is coulombs, but look, that distinction doesn't really matter for understanding what's actually happening. Okay, so, right, a voltage is a difference, it's a measure of difference across 2 points. What else do I need to know? Well, what you need to know is that actually there are 2 ways of us claiming that difference, right? For example, in this case here, if each unit of charge there has 9 joules of energy and each unit of charge has 4 joules there are actually 2 ways you can take this difference, right? You can take this difference as 9 minus 4, which is 5 volts, or you can take the difference as 4 minus 9, which gives you minus 5 volts, right? Hopefully you can see either one's correct, right? Both of them give an indication of the difference. Now, as a side note, sorry, I forgot to mention, the unit for voltage, right? Because it's a measure of the difference in energy for each unit of charge across 2 points, its unit, obviously, as intuition might suggest, is joules per coulomb, right? How many joules lost or gained per coulomb of charge? Of course, these days, we use volt, thanks to Alessandro Volta. Right, so there are 2 ways we can convey a voltage difference, a potential difference, which is a voltage, across a component, either in this case as 5 or negative 5. So what gives, right? How do I know which one's right? When you tell me, if I tell you the voltage across this component is 5 volt, that's not very useful, is it? Because I need to know, well, did you take the difference with respect to the top end or the bottom end? Are you using whatever the energy each unit of charge here is minus that, or are you using the energy there minus B, right? And that's why whenever you define voltages, you always have to, it always has to be accompanied by a voltage arrow. That's how we get rid of this ambiguity between 5 and negative 5, right? What that means, if you look over in the next page, by indicating an arrow with the arrow tail to be the point in which you're taking the difference with respect to, these are now conveying exactly the same thing, right? In this case, I'm saying how much more energy is those charges at A in comparison to B, right? How much more energy are the charges carrying there at A in comparison to B? Well, it must be 9 minus 4, right? Because the charges here carries 4 joules, the charges there carries 9 joules. So it's 9 minus 4 when I'm asking how much energy are the charges there at A with respect to B. And the tail end indicate the difference you're taking with respect to. Similarly over there, well, you're literally asking, well, how much more energy is the charges at B carrying with respect to A? Hopefully you can see the answer again. It must be negative 5 joules, right? The charges at B carries negative 5 joules more than those at A. Why is that? Because the voltage arrow I've indicated there says I am taking this difference with respect to A. I'm using whatever the energy the charges are carrying at A minus whatever the energy the charges are carrying at A. Did I say that wrong? I'm taking whatever energy the charges is carrying at B minus whatever those is carrying at A. And in this case, it's minus 5 joules. And equivalently, hopefully you can say that this means that the potential at B is 5 volt lower than that at A. So these two now convey the same thing. It doesn't matter whether you take the difference as negative 5 or 5 now, provided you indicate what you have taken that difference with respect to. And so the take-home point, voltage only makes sense if it's accompanied by a voltage arrow, right? Just like how a current only makes sense if you indicate a direction, right? If I say the current through this source is 5 amps, that doesn't mean anything to me, right? Is it flowing through it downwards or upwards? I don't know. Both in these two cases, they mean different things, right? Similarly with voltage. Now you might have noted that there's another convention for us to convey this, and that's using sort of the plus and minus symbol, right? These actually means the same thing, right? Does it matter which one you use? No, it doesn't. But, right, if I can understand both nomenclatures, I would hope at least you would understand it, because that's what I want you to get up to, right? To the same sort of understanding that I do. Right, so essentially this summarizes the thing down there, right? Both cases now identify the voltage across this resistor unanimously, right? Because voltage of 5 volt with arrow pointing upward, it's the same as a voltage of negative 5 volt with arrow pointing downwards. And so hopefully you can see that VAB here is the same as negative VBA. What we mean by VAB is the voltage at A with respect to B, right? That's what it means, VAB. Voltage at A with respect to B. So the voltage at A with respect to B must be the negative of the voltage at B with respect to A, because they're off by a negative sign. Now the most important thing, I guess, if you want to take away in this paragraph, is by expressing the potential difference, or the voltage, or the difference in energy across the component, we no longer have its absolute value, right? From this, all we know is the difference in energy across these 2 points is 5 volt. We no longer know the fact that the energy there has 9 joules of energy. Similarly, the energy there is 4 joules, right? If I only indicate the voltage is 5 volt, now that's a relative value, right? It's simply saying one end has 5 joules of energy more than the other. Any questions on this? You all look stoned. Is this too easy? Hands up if this is too easy. Hands up if you understood what I just said. Okay, that's good. So we're learning something new then, if this is not too easy. Right. Final thing. Look, one last thing before we go. And again, this is another common misconception people have about electric circuits in general. Shh. Thank you. And this is the notion of common reference, or something we call ground, right? Now, you would have met these two symbols before, or either or, right? Maybe you only seen one, or maybe you've seen both. They mean the same thing, right? If you want to be pedantic about it, usually we use the latter symbol for digital circuits, whatever that is. You'll meet it somewhere down the line. And we use the former one for analog circuits, such as the circuit we designed containing resistors and stuff, right? But for this course, look, it doesn't really matter which one you use because they both convey the same thing. What does this symbol actually mean? It literally is just a convenience for us. It's just a symbolic indicator. What is an indicator for? It's an indicator for things like, we tend to abuse these notations. You probably heard people say the voltage at this point in the circuit. For example, you might hear people say, if you look at the circuit down there, the voltage at B. Now, if you understood what a voltage is, which is a difference in energy between 2 points, it doesn't make sense to say the difference in energy at B, right? What does that mean? The difference in energy at B, right? A difference is between 2 points. You're measuring a difference between 2 points. So what do we mean by a difference at B? Well, that's why we use the symbol, right? Wherever we place this ground symbol, it's just a convenience for us electrical engineers to say, hey, look, whatever circuit I present down there, if I were to say a voltage at somewhere, it is understood what I meant is it is measured with respect to wherever that ground symbol is placed. That's it. That's all that ground symbol means. No, current do not flow to ground. Right? Ground is not an alternative path, right? You don't see charges flowing here and then it goes down to ground. No, right? That's not what a ground is. Ground is literally just a symbolic indicator where we are saying, if I were to indicate the voltage, say, at C, what I mean is the voltage there measured in comparison to whatever the voltage is at D here. Right? So then we know when we say something is at the voltage at somewhere, it's measured with the difference with respect to D. That's all it is, right? So it's simply a symbolic indicator where it provides a convenient reference in which voltage at various points can be measured with respect to. So if you were to look at the circuit down here, the voltage AD, which is the voltage at A with respect to D, is 10 volt. Now, because we have defined the ground there, sometimes we abuse that, right? Because it is understood, you know, whenever I say voltage at somewhere, it's with respect to that. So I could simply state voltage A, right? Single subscript A. It just means the voltage at A. And of course, when we talk about a difference at a point, it must be inherently with respect to somewhere. Where is it to? D. And that's why we could also say the voltage at B with respect to D is just VB. Notice these two things, VAB and VBC, they are not with respect to ground, right? Because if you infer what they mean, they just means the voltage at A with respect to B. That's the difference in energy between the charges at A measured with respect to B, right? That's not with respect to ground. But VCD is, right? Because that's saying the voltage at C with respect to D, well, that's the same as just VC, right? Because the other end is taken to be ground. And that's all it is, right? So you would have seen on the next page that I summarized that essentially, right? When we say the voltage at A is 10 volt, it is understood it means the voltage at A with respect to D. Final thing, before you all run away, notice the placement of ground is purely arbitrary, right? Given that you understood ground is just a symbolic indicator, it doesn't matter where you place grounders, right? Who's to say I can't place my ground there? What happens if I place my ground at C? It just means if I were to talk about voltage at A, for example, what I meant is the voltage at A now with respect to C. And in this case, I hope you can see that means it's 9 volt. If I place the ground at C and I indicate the voltage at A, can you see why that's 9 volt? Right? Because what does the 6 volt say? This 6 volt says the charges here carries 6 joules of energy more than the charges there. So that's whatever the energy here plus 6. But then that says the charges there carries 3 joules more than there. So that's 3 more than 6, which is 9 joules more than whatever it is at C. So if my ground is at C, voltage at A is 9. And that's what's indicated down over there. Right? And similarly for the other ones. Anyway, thank you. And I'll see you tomorrow as we march on.
Yeah.
You guys keep on talking, that's okay. Got a few more minutes. Go ahead. All right, guys. Before I introduce myself and we get going officially, I need ideally one boy and one girl to be the class rep. An honored privilege. Is there anybody who would like to take a form, one girl and one boy? Yeah, I have one girl. Who would like to be the boy? All right, done. So you two, I just need that back at the end, okay? All right, welcome to Property 102. This is Introduction to Property. And who in the heck am I? Dr. Michael Ream, that's my name, but one thing I love about New Zealand, I'm sure you guys can tell I'm not born and raised here with my funny accent, is the laid-back nature. It took me a while to get used to it, but now I'm all cool. I'm all sweet as. So you guys can call me Mike, okay? I'm not going to say it's a privilege, but I prefer you guys just call me Mike. If you can't get past that and you say Dr. Ream or Dr. Michael, or I've gotten all kinds of things, that's okay. We could live with it, but if you guys could just call me Mike, that's how I'll address you in email and stuff like that. So my background, originally from the U.S., originally from Chicago, Illinois, not the big smoke, but the suburbs of. Most people in places like Chicago, big cities in the U.S., really live in the suburbs, not in the proper city. So I lived around Chicago. And when I was going to school, I had no earthly idea what the hell I wanted to do. I liked drafting and a few architecture-related stuff, so I ended up, my dad was a chemical engineer, still is a chemical engineer. He got laid off right when I was finishing up high school, and he moved down to Texas. And since I had no clue, and I didn't want to pay for uni myself and all that, I just followed him. And I went to Houston, Texas, and decided to study architecture. So I did 5 years, it's a 5-year program there, and got a degree in architecture. And partway through, and you guys might follow the same kind of path, you'll be like, what the hell was I smoking when I signed up for that program? And then I decided, okay, I really don't want to be an architect. I did work for a little while, and then I went back to uni and got into property. So it took me a while to get where you guys are. Not that it might not be perfect for you, but whatever. I ended up in the same space for a master's and then later a PhD in property. So I went from architecture into essentially real estate. Now, when I was there, I met a beautiful woman named Olga. And if you guys are going to continue on and do the full B-Prop, you'll probably have her next semester in Property 251, which is Property Finance and Investment. She's a colleague of mine here. And we met at Texas A&M University when we were doing our property degrees there. We ended up doing the same master's and the same PhD. She was from a place called Kazakhstan. Now I'm just going to flip to the next slide. It used to be easy. I just say Kazakhstan. People go, oh, Bharat. So if you know what this guy is, yeah, Bharat. He's from Kazakhstan, supposedly. He's not really, but anyway. So she was from Kazakhstan, and I had no choice. If I wanted to be with this woman, I had to go to Kazakhstan too because of the scholarship she had. The U.S. was going to knock her out of the country, and she had an obligation to live in Kazakhstan and work there for a while. So I ended up there. I was young. I had no idea what I was doing other than I was following this woman. Probably if I was older, I would have never gone. But it was cool. I worked for a Brit and did a lot of real estate consulting. And anyway, it was a fascinating time. Our 2 youngest children were born there. And then in 2005, I came here. And this was my first academic gig, and I haven't left. As far as just other interests, I'm into sustainability. You'll see a little bit of that in this course. If you continue on in property and you take my stage 2 paper, Building Construction, you'll see a lot more of my interest in sustainability. Leaky buildings, research in that. Also own a former leaky building, and again, that'll come through in the construction paper. Do quite a bit on GIS, which is just digital maps, location, different analysis, and I teach a post-grad paper in GIS. And more recently, I've been doing a lot of consulting-related work on housing affordability. There's something that's going to come out in Uni News. I know it's not something you guys probably ever read in your entire lives, but you might come across it. It's a publication by the University of Auckland, and they do a feature at the back end, I think. And it's a little article that I wrote, and the topic is mainly on housing affordability and something that we're going to touch on a bit in this course. And I know it's something that it should be of importance to you guys because it's quite a challenge now in New Zealand to be able to actually afford your own house before you're older than me. Unfortunately, it's a difficult situation in terms of housing affordability, especially in Auckland. So I'm looking into that. I'm researching it. Can't tell you that I'm going to solve all the problems, but I'm doing my best to be able to get you guys to be able to afford your own home because I think you should be able to. So we'll skip past Bharat. As far as the focus of this class, well, property in its nature is multidisciplinary. You look at the different courses in property that we cover here, every one of them is kind of a major in, say, commerce. So we have management, economics, law, marketing. Those are all they're entire disciplines onto themselves, and what we tend to do in property is we have to deal with all kinds of very complex concepts, and then we use them to solve property-specific problems. And of course, it's so multidisciplinary that it goes beyond even, say, this school. So the course that I mentioned I teach in Stage 2, Building Construction, and part of what you're going to cover in this course is a bit of the built environment, construction, development, property development. So it's not only multidisciplinary, but it's both a physical and a financial thing, which is quite bizarre. We are kind of the black sheep of the family in this school. The business school doesn't know what to do with us. When we were in architecture, when I came here in 2005, I think 2 years prior, we left architecture and we came to the business school. It was great for us because suddenly we were on the radar. Lots of students suddenly knew, whoa, property is an actual thing. When we were in architecture, we were the evil capitalists. I mean, literally, the people there hated us because we were the money-hungry, awful people. And we come here and we're just, oh, okay, they love us, but then they're like, what the hell are you doing with like this building carpet and stuff? I mean, they didn't quite get us, and they still don't get us. We're the tiniest department, but as I'm going to explain in the first lecture, on the overview of the property industry, is property is extremely unique. And one bit about it, it's multidisciplinary. Another bit is that it deals with the built environment, which you have to kind of understand if you're going to succeed in property. But equally, it deals with finance. You got to make money, and money pushes things around. And a lot of the decisions we make in any form of business, including property, deals with money. So that's the basic nature of the class. As far as the approach, because especially in the first half of the course, but I use visual stuff all the time. I try to keep things visual, especially when dealing with the built environment, because I think you need to see it. Ideally, you're out there physically seeing stuff, but there's almost 300 students in this class. There's just no way I'm going to get you all onto a site or do any of that fun stuff. So we'll have to do it through drawings, imagery, video, and stuff like that. But I'll do my best to make it as real as I can for you, because I think it's important. Now, some students in the past have asked, especially when you get down to like the built environment stuff, why in the hell do I need to learn this? Well, if you're going to go out and be a developer, property developer, or if you're going to, say, be a valuer, which are two, very popular pathways for graduates of this program, say you're driving along and you see a potential site. It's an old derelict building in a good location, and you have an idea that I could actually either knock that down or redevelop that site. I could do something cool with it, add value, and make money. All things great. Now, you're not going to go screaming out and immediately and engage an architect and engage an engineer and a planning expert and all of that stuff and start spending money on it. A lot of the initial stuff you're going to do, it's kind of called back of the envelope. So scrap piece of paper like this, you're just going to jot down some ideas and do some calculations and use the things that you would learn in the Bachelor of Property to make some initial decisions. Now, if you click the go button and say, oh, okay, my numbers work out, I think this is a go, then you will go ahead and engage those people. You get equity investors, big money bag people involved and whatnot, and then the project will continue on. But all the initial stuff, you have to do it based on your own mind, and those are the kind of tools that you'll learn throughout the program. And part of those tools you'll learn in this class. So if we look at the organization of the course itself, we'll start off with this overview. Okay, that's lecture number 1. I've put Maori land issues in there, and we'll talk about how that's actually delivered. To be honest, I don't know yet. There's a guest lecturer, one of my colleagues, that will come in and either speak physically here, or she has threatened to put together an online lecture, purpose-made lecture. We'll see if that happens, but we'll figure it out. So anyway, overview, what's going on in the property industry, yeah, so a broad overview. And then we're going to hit the physical side first. And a lot of the application of the concepts we're dealing with is dealing with residential construction or residential property. So the first bit I'm going to cover with you guys is essentially how to build a house, the nuts and bolts of the physical thing that is residential buildings. That kind of takes up the first half of the course. We hit a test after we come back from the break. And then the last few weeks, we talk about the financial side. So property valuation. Again, focusing on what are the attributes that make up the value of a house. So what are the determinants of value? How do property valuers figure out what a house is worth? And to a certain extent, what is value to an investor? What is investment value? And I'll go through all the different aspects of what value is. So that's kind of the focus of the second half of the paper. And then the last week, I'll invite people from the industry, two organizations, the Royal Institute of Chartered Surveyors will come and do a little promo talk to you, and the Property Institute of New Zealand will also give you a bit of a chat of how their organization is awesome and is something you'd want to be part of when you get out. And then we'll cap it all off with an examination review. So this is a bit of a snip from your course outline that you would have in your course books. Or course books, I'm not seeing too many. Yeah, there's a few course books. They must be available for purchase. The electronic version, a PDF of the entire course book's also on Canvas if you want to just download it, print it yourself, or just have it as an electronic copy. So you'll find this on Canvas or in the course book. And so what I'm trying to explain here in this little graphic is this course is quite different than most uni courses. I've adopted both in this one and in my 200 level course what's called a blended learning approach. So the idea is, instead of me sitting up here being the talking head, and spewing information to you, I've captured all that talking head stuff, I've edited it so it's much more efficient, and I've put it online. And so there's a whole bunch of little sitcom size 20 to 40 minutes. I try to get them down to 30 if I can, but some of them honestly are a little bit longer. And they're available for you guys to engage with and pause, take notes. There's a lot of advantages to it. And then what we do is we focus on recovering the material that you're absorbing in your own time here in this room once a week. And we'll do it for 30 minutes, an hour, whatever it takes. We'll have some fun. I'll kind of get into how it all runs. But essentially, lectures are delivered online. Frees up all your time. We don't have to come in here very often. And then we just do these what I call review sessions, which are kind of like tutorials, and they're interactive. I'm asking you questions. We're having a bit of fun. There's some prizes involved, all kinds of excellent stuff. So it's a different kind of course than what you're used to. All right. So what I'm trying to highlight here, and it's pretty straightforward, is like, say, take week number 2. Week number 1, it's just this introduction lecture, and then tomorrow we're going to have a welcome from the rest of the department. So the head of department will come up here and say hello to you, and then we'll queue up like a, usual suspects, a lineup, and we'll all kind of like sit there, and they'll say, you would like to say anything? No, we don't want to say anything. And then we'll move on, and some other people will talk to you. That's tomorrow. But really starting from week 2, you're going to see me once a week, and what we're going to have to break out of is, right now you guys are awesome in terms of being really quiet. That's awesome. For a lecturer, this is gold. It's a real pain in the ass if I have to constantly say, you over, I don't mean to point at you, I'll point over there, okay? You over there, stop talking, okay? But what's different about blended learning is I actually want you guys to be talking, and I think it's kind of horrible to be completely dead silent like this. Right now it's okay, because I'm talking. But as we move forward in this course, I would like you guys to be talking to one another, because I'm going to be hitting you with questions. Questions are going to come up there, and we'll get into this. You're going to be using Kahoot to answer those questions. I'll see you guys answer. I'll go, oh my God. And then I'll try to explain to you why the answer is what it is, and then we'll kind of go through this process. I'm going to be throwing here. I'm just going to try this. There's no payload in this, so it's not going to hurt. So who wants to try to catch this? The very first one of the entire semester. You? Okay, here it comes. All right, now throw it back. Awesome. So this is going to be one of our little tools. I only brought one little gizmo. This is just a stress ball cut open into a little Pac-Man, and I've corded out a little bit. We'll get into it, okay? These things will have candies in them, all right? And this will be our little prize system on rewarding the people who do the best in our little games that we play every week. So every single week, say week 2, there's a series of lecture videos on Canvas. You watch those, you take some notes, you learn, and then we come in on a Thursday and we cover essentially that material. We can't cover it all, and I'll specifically find stuff in there that I think you guys need to brush up on a little bit, okay? And again, I'll explain it as we go. So we have these review sessions at the end of each week, and during the week, you're kind of digesting lecture material online in your own time. Often students do it in the evenings. You could do it during the class time if you really want to. Almost nobody ever does. You do it whenever it suits you. You have to have watched everything by the time we start our review session. Okay, that's important. And I'll get into it. So that's the structure. Okay, here's all the different lectures. Yeah, there's your big test. All right. Have a couple review sessions before the test, specific to the test, so test review and exam review. Anyway, we'll go through it. There's nothing super complicated here. Like I mentioned before, lecture number 2, I don't know yet whether that's going to be online or whether it's going to be in this room. What is that, a week from today? No, 2 weeks from today. I don't know yet. I'll let you know. So keep your eyes on Canvas announcements, and most likely it'll be online just like all the other stuff. That's what I've kind of agreed with the guest lecturer. So as far as marking, there is sections of your test and exam that are going to be a bit subjective. I'll always mark that. Short essays, things like that. I'll try to always give you partial credit. I won't be mean. All the objective stuff are pretty much automated. Now, in the past, I have had markers that I employ, I train. So, you know, I don't know if I'll do that this semester, but just to give you an idea of who these people might be. Here's some of my past markers. Yeah. So that's our firstborn, Linda. Yeah, she's pretty ruthless, but Sasha with that pen, she'll just absolutely butcher you. So now there's a reason other than getting the laugh. You know, got to have the laugh, but there's a reason why I show this. This is a more recent picture. When I was a student, I literally thought the people who were up at the front of the room were some kind of robot, or they weren't really all that human. And I just wanted you guys to realize that the people who do stand up here and lecture you are human. We have families and all of that stuff. Anyway, we're not mean people. We're very approachable people, and we really want you guys to succeed. I can't say that, you know, you guys aren't going to be my family. You know, they'd be lying to you. You know, you're not my kids. I'm not that productive. But I do care about you guys, and I do want you guys to succeed. So I never want it to be like a me versus you situation, all right? It's not like I'm going to bust your ass in the test and I'm going to feel good about getting so many C's or something like that. If all of you got A's, I will take the heat. I will go to the dean myself and say, hey, I'm just that good, you know? So anyway, I want you to know that I'm human. By the way, this is an old photo. Linda, I sat there even today. I was like, you know, should I show them the new folder? And I decided not to, because Linda's now almost 17, and I'm thinking, you know, I really don't want to go there. I don't want to show these guys in the room, you know, my daughter. She's going to be sitting out here in a couple years. Probably not going to take property. She wants to do medicine. But so Linda's almost 17. Sasha's almost 15. Jason is just turning 8 this Sunday. Karen just turned 11, and then that's Olga, the one that teaches the finance course, my wife, and that's me. You'll notice in the videos, you're going to see younger versions of me, heavier versions of me. I didn't miss too many meals at that time. Anyway, so there you go. I'm human. You know, do think about that. Not just me. I'm not the only human. Not everybody else is robots. We're all human. Yeah. So just keep that in mind. And we're approachable. We're not mean people. We want you guys to do well. So how do you approach me and find me? I used to do office hours and stuff, but it's just, you know, for me to sit there, you know, wondering if somebody's going to show up. You guys never show up. So what you guys do is you just show up when you feel like showing up. So I'll be sitting there, I'm like, hey, you got a second? I do now. Yep, go for it. Ideally, I don't mind that. Ideally, you guys shoot me an email and say, hey, and we agree a time that you show up to talk about something. Or at the end of a review session, before a review session, we can have a little bit of chat. But this is my office. Here's my email address. That's the best way to get a hold of me. You could try leaving a message or whatever. I'll call you back. But anyway, this is where you'll find me. I really like visitors. I used to get so many more, and it's not because well, maybe when I started lecturing, I was 29 years old, and I'm more than 29 now. So maybe I don't relate to you guys as much as I used to. But I just think it's just part of the way students have evolved over the years that I've been lecturing. Just people don't ask too many questions in class anymore. They don't come up and visit in office hours or at all, or before or after. But that's cool. I could engage with you guys however you want to engage. And I definitely like face-to-face contact in office hours. Or during whatever. Just shoot me an email. We'll figure it out. I'm always available. As far as readings, there are no required readings. What I do in the course outline is I give you some textbooks that I've basically used to develop lecture material. You're more than welcome, if I'm talking Japanese to you guys in the lecture and it's like, what the hell is he talking about? If it's going to help you, you might want to refer to the actual source. Most likely, if my stuff is Japanese, that will be some other kind of, crazy language, Latin. But anyway, feel free to all these are in the library. Some are totally online. But there's all kinds of sources out there. None of them are required. What's required is your course book. And a lot of you have already purchased it. That kind of thing is required. That is your little Bible, okay? Take notes. There's lots of material that comes in addition to what is printed in the course book. As far as course admin, okay, Canvas is a very important tool. There is a 20% test in this course. It's going to be computer-based. Now, the current population of this class is pushing 300, and there's no way I have enough computers. So I'm going to have to figure out a way to solve this problem. I don't know if it'll be enabling some students to take it online. There's a proctoring service, US-based, that I've used in the past. I don't know what the solution's going to be. Another option is to kind of use this room and have some of you guys self-opt into doing paper-based versions of the test. Some people are over in the computer labs, some are here. It's a problem yet to be solved, all right? But I will have to figure some way to administer this test all at one time. It's going to be not during class time. It will be in the evening because we're going to be using all the computer labs. Check Canvas, like the Maori land issue thing. Make sure you find out whether we're going to be here physically or whether it's going to be online like the other stuff. Okay, assignments, they're all uploaded to Canvas. There is an Aropa thing as well. We'll get to that. And I will be as quick as I can to get marks up. I know you guys like to get your feedback and your marks quick, and I'll be fairly lightning quick. As far as the online lectures, I call them modules. Okay, these are just video lectures. Like I said, I try to break them down into bite-sized pieces, 30-minute sitcom level, something like that. They're all served up on a computer here in the business school. If you're watching them in the building, super fast. But even at home, it should be all fine if you have a decent internet connection, no problem. Watch them 24/7 whenever you like. If you're going to watch them in a public space, please use headphones. I mean, people don't want to listen lecturing from me, all right? Don't want to share that. And again, you can rewatch it as many times as you want. Anyway, super flexible. So that's kind of a blow-up of the anatomy of one of these things. There's a little bit of a picture-in-picture thing, so I'm talking to you. I'm trying to look at the camera. Some students think that it's a bit strange. It's all psychological, I guess, that because I'm talking to you, looking at the camera, you feel like, oh man, Mike's actually talking to me. It's kind of neat, rather than the person way out in the middle of the corner of the room. Some people just would rather not maybe put a little piece of paper on there or hide me or whatever. But most people, I think it's a bit engaging and makes it feel like a real lecture. There's some closed captions down at the bottom. Now, I've had students in the past they're all about jacking up the speed to chipmunk level. I'm like double the speed because they just don't want to spend any time dealing with me. And then they'll put the closed captions on, and they're just freebasing information as fast as they possibly can. If that works for you, awesome, you know? I've never had one student ever slow me down, yeah? It's never gonna happen. Although you can, but nobody ever does. So use the closed captions. You can do keyword searches. I don't know if many students use that, but use the pause button. Most valuable thing in this whole system is to be able to pause. That's not something that, I mean, yeah, you could, somebody say, hey, can you please, but nobody ever does that in a live lecture. You guys can pause it, you can rewind, what the hell did that, what did he say? And go listen to it again, skip around, do whatever you want. You have all the control in the world. There is, and some of the videos have more than others, there are little pop-up things. So like if I'm talking about something, again, I'm using, especially in the built environment stuff, the construction portion, I'm using images, but sometimes there's just no way an image is going to do it justice. So I will have gone and I've gotten YouTube videos, and so there's some things that might help you understand a concept that's in video form, and I've plugged that in there, okay? So you click on that, whoop, off go to YouTube, this thing pauses, and yeah, so there's all kinds of content for you to go through. Use the pause button, take notes, very, very important. At the end of each one of these little 30-minute things, videos, is a quiz. It's not marked. The whole idea is there to test your own knowledge of like, okay, did I actually learn something in this 20 minutes? Can I answer these questions? If you get them all wrong, well, it's not the end of the world. You could rewatch it. You could take it again, take the quiz again. The quizzes form an important part of me being able to provide you with participation marks to kind of keep you honest and help you with your own time management. So they do a lot of things, these quizzes. They'll check yourself, but they're also an incredibly important tool for me to be able to reward you for watching the content, keeping up with the material. All right, so each one of these quizzes at the end, I've told students over and over the years, put away your course book, take the quiz like it's a test. And still half the students are like, hell no, I'm gonna go back, I'm gonna find the damn answer, because I'm gonna feel better if I get the damn thing right. It's like, okay. Again, it's all psychological. So whatever floats your boat, you could go ahead and do that. My suggestion would be to be honest with yourself, try to take the quiz, there's no marks, and just see if you can answer them. That's it. It's probably the better way to go, but it's up to you, okay? All right, ooh, the assessments. Oh, I know you guys are all over this. So we'll have a test, yeah. That's the first portion of the class, lectures 1 through 7. I think it's 1 through 7. Anyway, have to double check that. It's the built environment and the overview Maori land issues. That's what it is. There is a 5% assignment, which we'll talk about briefly, and then there's the larger 15 plus a 20% overall evaluation report assignment, and we'll talk through both of these really briefly. And then there's 5% kind of free marks, as I like to think of them. You guys, I know, earn them. They're not free. But that is me helping you with your time management, me keeping an eye on you and seeing if you're watching the videos before we actually meet to review things, whether you engage with me via Kahoot in the review session. So I'm going to pay you 5% of your grade for free if you do that. And then at the very end, there's a little bit of a feedback survey that I've done over the years, and I pay you for that. I pay you for everything in this course. And then the final exam's worth 50%. Now, one thing that's important is the policy, the Department of Property policy on final exams is you have to score 45%. Now, last year was the first time we had that, and I had an essay question, and I will do this in my test and in my exam, and I'll usually put one juicy, beefy essay question in there, and it'll have a decent amount of marks compared to the rest of the assessment. And I told you guys, not you guys, sorry, the previous group, I said, okay, it's going to be on this lecture. Yeah, it's going to be here. Make sure you review it again. And some people just completely fell to pieces on the exam, and that alone knocked people into this 45, below 45. So they did actually okay with everything else. So it's a pre-warning for you guys now. I will do what I can to be really cool and provide you enough wink, wink, nudge, nudge. Hey, you better look at this 4 times. Yeah, I'll do that. But if you guys ignore that, man, when it comes to the final exam, you can actually, I won't tell you what their grade was before the 45 kicked in, but some of them were really ugly, yeah? But it's a policy out of my hand. That is the department's policy. You know, you might be going through a B average. It's like, woo, and then that's it, yeah? It could happen, all right? All right, so as far as participation, making that free 5%. So again, there's quizzes at the end of each one of those videos. When the video comes up, you're gonna get a little box like that. Put your name in there, all right? The name is actually not so critical, but I would appreciate, it makes life easier for me to deal with the data if I get your real name. And then the absolute critical thing is the email address, okay? And that has to be your University of Auckland email address. Particularly the first part, which is your UPI, has to be typed correctly. You screw that up, I've taken a former student of mine, he's a whiz-bang person with computers and all that, and he made software, a little Java program. And I use his software to process all the data in my courses. Man, it'll just eat you up. If you put in your Hotmail account, you screw that up or screw up your UPI, it'll just eat you up, and your record of viewing that stuff is gone. Yeah, it's toast. So I'd hate for that to happen to you. So be very, very careful and enter your email address right. Yeah, it has to be University of Auckland one. The UPI has to be at the beginning. Absolutely critical. All right, so here's some of the rules and regulations. I wish the system was really super clever and the computer can just tell me honestly whether you watched or not. But I know the tricks, you know. It's like a game of cat and mouse a little bit with students, you know. First time I do this, the students figure out, oh man, I could do this, and totally, you know, like one of the classic ones is, you know, that commercial with the guy spray and walk away, yeah. So it's like hit play and walk away, you know. So that's what I've had students do, and the thing that I found students did is like, you know, I could hit play and walk away, but hell, I could hit play 6 times simultaneously and let them all run at once, you know. And so I've had to put in countermeasures against students' ways of getting around my system here. So I'll tell you now, do not do that. Do not watch simultaneously any 2 videos. Even if you're gonna load them up because it's more efficient and, you know, it saves you a few seconds or something like that, do not do that. Load up a video, put in your name, watch the video, pause the video, watch the video, pause the video, get to the quiz, take the quiz. Load up the next video, put in your name, and so on and so forth. You know, always, always, always make sure you attempt the quiz. The way the software that I use to produce these video lectures is there will only be a record that I see a viewing session from you if you submit the quiz. So if you got a 40-minute lecture and you're like, oh, you're halfway through and like, man, I just can't take anymore. Okay, skip to the end, do the little quiz, then come back later and then watch the second half and do the quiz again. No big deal. But if you skip or just never do the quiz, I'll never have any record of you guys watching anything, okay? So it's important, and you'll see, right now you're not gonna get it. The first week I'll be really, really cool with you, and then I'm gonna start cracking down, and you're gonna be like, why didn't I get marks? Why didn't I get marks? And then I'll explain, oh, you didn't listen to that first lecture. That's now recorded, and it's gonna be on Canvas, okay? So you have to make sure you don't skip, you watch the whole thing. This is important. If something happens, power goes out, something you skipped and something went weird, there's a little form that I've created on Canvas. Just go ahead and fill it in, say, hey, Mike, man, something happened, or whatever. And I'll look at that every time I kind of pass judgment on your participation marks. But if I don't see a little form submission, I'm not gonna know. I'm gonna assume that everything was hunky-dory, everything was cool, and you just didn't watch it, all right? So if there's a technical glitch, whatever it is, even if it's just your own fault, who cares? Just fill it in, and just a little explanation real quick. It will just take you a second, and then we'll all be sweet. Okay, as far as the review sessions, how many of you guys have used Kahoot before? Awesome, very good. Okay, so you're all professionals. Okay. So there's 9 review sessions, and we'll be using Kahoot the entire time. Now, one thing that's different about Kahoot, and I've learned this with Kahoot, okay? Now, I throw out chocolates, this little gizmo that I use, these little things, right? But I know what students really like. One big prize, you know what that prize is? It's to have your screwed up, cool, whatever name show up on the board. That is probably more valuable than whatever I'm throwing out. So I've actually taken my time and I've made 2 different levels of Kahoots. Okay, one I call discussion questions. So I'm looking at those quizzes you guys are doing and I'm saying, okay, they screwed up on that question. Man, they totally screwed that one up. And then those are the ones I'm going to try to ask again in class. And then I'm going to do a little lecture, say, well, this is why it is, this is. And then when we're done with their discussion questions, and that's going to be important that you kind of attempt at least half, like I you say here. Attempt half of those, because that's kind of the review session. And then we park that and say, okay, now we're going to have our little tournaments. We're going to run some additional Kahoots. That's when you could go with your super creative, try not to be incredibly vulgar, but whatever. We're all adults here. We can handle it. And then we'll run tournaments, and that's when we throw out the chocolates and we have a bit of fun. So we'll do a little discussion questions. That has to be your UPI when you do your little nickname, because otherwise I'll have no idea who you are. And then we park that. Tournaments, you guys go for broke and put in whatever kind of crazy names you want. All right. Now everything is live streamed. Can somebody be my awesome volunteer and go to Canvas? There's a little link to the live stream. And just see if the live stream is picking this up. You don't need to sit there and watch it or anything like that. But if somebody, I had the IT people re-engineer these little lectern things, and they put some secret software. I can't even tell you where it is because it's too top secret. And I could actually live stream to a YouTube page, and that's what this is. Is it live? Yeah, awesome. Okay, so we're live. So this is go. And I'll be live streaming all of these sessions. So if you guys are like, man, I can't be bothered coming into uni to do Mike's thing, chocolate and all, I'm just not going to do it. That's cool. Just go to live stream, yeah? Because if you don't go to live stream, you know, to be honest, I know how Kahoot works. You can just say, today's color is yellow, and just, you know, you don't even know what the question is. Okay, I'd rather you not do that. Take advantage, go to the live stream with the discussion questions, you know, listen to the, you know, I'll explain it, we'll have a bit of laugh, see how you guys do, you know, and you're participating at home. Use the live stream if you want to participate in in these sessions at home, all right? So a combination of live stream and Kahoot. All right, so again, I've already mentioned this, student feedback at the end, total 5%, all right? I will be fairly generous at the very beginning of the course, but then I will start cracking down when it comes to participation marks, all right? They're 0.5% a week. I mean, come on. We're not going to get in a big debate between you and me on that 0.5%. If you guys screwed up or something, the software's passed judgment, you didn't do it, let's just leave it at that, okay? So at the end of it, if you want to earn your 5%, you got to properly, fully, yeah, not overlaps, all that stuff that I've talked about. Make sure you watch these video lectures, and you got to do all of that by the start of the respective review session when we're supposed to review that material. And on top of that, you need to answer half of the discussion questions that we ask that I ask you guys in Kahoot. Okay. As far as the assessments, again, we have a 5%er, and this is it's kind of like a scavenger hunt, really. I give you a list of items. This relates to the built environment section of the course. They're all kind of residential related, and rather than you guys going onto YouTube and Googling it and giving me a picture of it, you know, I want to make sure you actually found it somewhere in real life. And so you have to take your picture with this thing. Or if it becomes too difficult to take your picture with it, then you could use your student ID and take your picture like that, okay? I'll show you some examples. It's an individual assignment technically, but I always encourage students to do it in groups. If literally all of you guys can coordinate yourself to do a picture with every single one of you in there, then you guys can all submit the same picture for that item. If you could pull that off, I'd be very impressed. All right. Usually you'll have groups of 3, 4, something like that. It's common. Whatever you could squeeze into a car, then drive around and go find these things and take photos of them. All right. Do not go onto private property. You don't just flash your student ID and say, hey, do an assignment. No, don't do that. You're going to get me in big trouble. All right, don't jump a fence. Don't do anything like that. Okay, don't do anything illegal to get your photos. Okay, Feel free, although I shouldn't say this, I do this every year, so I might as well tell you. If you're sitting there going, oh, I've taken some photos and there's one that I just can't get, shoot me an email and say, is that marble? You know, and I'll, you know, don't sit there and say, can you please grade my whole assignment before I submit it? No, I won't do that. But if there's one or two photos you're kind of iffy about, go ahead and submit it to me. Just email it to me and I'll give you the feedback. Okay, the second assignment is later on in the semester, and to be honest, you won't find any instructions yet because I still need to revise them. I've had feedback from the last couple of years that I've done this assignment, and I'm going to try my best to provide you guys more guidelines and a bit more hand-holding, okay? Now that's a double-edged sword, so you're aware. The more hand-holding I give, the more perfection I'm going to expect in your assignment. So if I give you a bunch of vagueness, I'll let you kind of, you know, whatever. But if I'm giving you very, very tight instructions, then I'm going to expect very, very good outcomes. So anyway, what this assignment is a due diligence report. The idea is, it's fictitious, everything is fictitious in academics. Essentially, you have a partner. You want to buy a house. The house, you're a first-time home buyer, the house might not be ideal to live in. Maybe you could rent it out. You don't know. You're a bit on the fence. But your partner's like dead against it and is like, man, you're just smoking crack and I don't want to deal with you right now. And so you're trying to convince your partner and say, man, come on, it's a great idea. Please, 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 hence the photo, right? So you're putting together this report to convince your partner to go ahead and in this purchase with you. And I make it really lovely for you guys. You know, I'm all about trying to stop plagiarism and stuff. Not that you guys are all going to do that, but so I assign you a unique property, every one of you. It's a bit of a pain for me, but it kind of ensures we're all kind of honest with one another. So everybody's going to get your own assigned property, and so your property will be unique. All right. Anyway, we'll get into this a little bit later in the semester. That same assignment has a second part, and that's peer review. All right. In the past, I had students peer review only a small number and have to give some kind of feedback, written feedback. I'm going to try it a different way this time. You're going to do double the number, but it's just going to be a rubric-based kind of, you know, on a scale, no written kind of open-ended feedback. That's kind of where I'm at right now. All right. Now, not only are you going to do some rubric kind of, yes, they did this great, they did this great, they did that, you're going to have to give a letter grade. We all know letter grades, A+ to D-, right? This is the spectrum. You're going to have to grade each one of these assignments, and you're going to be limited to how many grades you divvy out. You can't give 8 A+. You can't also give 8 D-. You have to spread the wealth across the people you've been assigned. And all of this will be fed into me, and it'll help me assess you guys. So you're going to get a grade, 8 grades from your peers. You're going to get 1 from me, and there you have it. So you'll get all kinds of feedback on that one. Okay, here's a bit of past student work, okay? Now you guys do not have to dress up and be odd. But this is just the first assignment, some examples. So again, rusticated weatherboard, here he is, he's in the shot, boom, yeah, okay, I don't think CMU is one of them, but whatever, you see, I'll show you some better ones. Trying to protect the innocent. Yeah, I put the black thing on there. So here is, again, this is commercial, but anyway, doesn't matter. Same concept. Here's a photo, and then they went ahead and did a little picture-in-picture blow-up. It's up to you, the onus is on you to convince me that you know what you took a photo of. Don't just have some massive ramble, yep, there's some timber in there, you know. Go ahead and find it yourself, you know. No. You need to show me that you know what you're talking about, all right? So if you got to do little arrows, picture-in-picture, whatever it takes, all right? Here's an example of, it's a gully trap, so that's one I think on you guys' hit list. So again, that's going to be a little bit odd. It's on the ground, you know, to sit there and take a selfie of that. No. So that one you might just go ahead and put your ID cards. Now I've had some students, they literally took like a ruler and they taped, I don't know, it was like 15 ID cards. They're just going around like this. I'm like, okay, come on, no. I know they paid you for that. Try not to do this, you know. Don't do the whole tape thing, you know. Come on, do it a little bit more serious. Okay, try not to molest some of the things that you're doing, you know. If you do it as a group, awesome, you know, that's great. Do it as a group. Yeah, like I said, the more people, doesn't matter. You all have to submit you can submit the same photo. It all has to be an individual submission, but you can use the same images. If you're in it, you're in it. It's all good. Okay, last slide. So to recap, what am I expecting from you? Okay, I expect you to attend either physically or virtually all of our review sessions, all right? And attend and interact in them. Answer questions that I pose to you. Whether you win chocolate, I mean 300 in this class, your probability is, you know, you'll see how I do it. I do try to give chocolates away and prizes away to people who actually don't win. Because what ends up happening is we'll do the thing, and there'll be the leaderboard. I'll say, okay, where is this person? Well, they're at home in their pajamas. So they don't get any chocolate. So there's opportunities for me to give chocolates. If you show up, your chocolate ability is increased, you know. Watch lectures, watch them on time, watch them legitimately, and then watch them by the time the review session starts. And like I said, engage while we're here. Bless you. Make sure you're not noisy, but you're talking. If it's dead quiet in these review sessions, it's a bit of a bummer for everybody, including me. So talk to each other. Again, if there's a question up there, it's like, man, what is it? Usually they'll have somebody who's like, it's bread, or whatever, you know, they'll throw out something wrong. Don't listen to everybody, but sit there and talk through the answers and figure out what it is, all right? Come and see me if you have any questions, and at the end of it, please give me your honest feedback. So those two who I gave forms to, if you guys can bring them up to me, we'll see you tomorrow for the welcome of the department, okay?